Hi everyone, my name is Qiao. Today I'll talk about how we improve VM availability at Azure. This is work I did during my MSR internship. Infrastructure as a service is one of the largest cloud services today. Getting customers' virtual machine up and running is arguably one of the most important goals for a cloud provider. Yet, getting to 5 nines availability proves to be challenging. So what is the availability bottleneck, and how do we eliminate it? In this talk, I try to answer these questions in the context of Azure. So before I get to the availability bottleneck, let me first describe Azure's architecture. So inside the data center, there are tens of compute and storage clusters that are connected by a cloud-like network. One key design decision is to separate compute and storage physically. What that means is that for virtual machines and their storage, which are those virtual hard disks, they're being provisioned from different physical clusters. The hypervisor is then now responsible for intercepting and redirecting the virtual disk access to a remote storage service. The key benefit of this is to be able to keep customers' data available during any localized power failure to a rack. However, this does also introduce a new type of failure, which we call VHD failures. So now VHD access has to depend on components from different subsystems. So if any one of them goes wrong, the VM wouldn't be able to access its storage. While the hypervisor can retry in order to deal with transient failures, it cannot do so indefinitely. In fact, after a certain amount of retry, by design, the hypervisor will crash the VM in order to surface the underlying failure to the customer, so that the customer may be able to take some actions to keep the application level SLAs. So how much does that actually impact VM availability? To answer that, we did some measurements. We look at unplanned VM downtime for a whole year and classify them by their root causes. Our main finding is that VHD failures account for more than half of unplanned VM downtime. In fact, for some of those failures, they can take tens of minutes to even hours to localize. So as it turns out, VHD failure localization is the bottleneck. So let's see why is it slow and inaccurate. So Azure SREs have known about VHD failures for a while. While it's relatively easy for them to detect that there's a problem, what's hard is to be able to pinpoint which component and which subsystem is responsible. So typically when an incident happens, SREs from different teams will check the local systems for any anomalies that correlate in time and space with the ongoing incident. However, this method can cause a lot of false positives, causing the instance to get pinpointed among different teams, losing precious time to fix the real issue. Furthermore, we have seen that the network and storage components can fail in unexpected ways. For example, they may go into a trouble state, but are not totally down. And one symptom is that they only fail a subset of VMs. And from our experience, this sort of gray failures can take hours to localize. So our key insight is that rather than asking SREs from different teams to check for local anomalies, what we should do is to actually take a global view instead, by examining interactions between different subsystems. Let me use a very simple bipartite model to explain the intuition. Let's put the compute clusters on the left-hand side, and then storage clusters on the right. We will join an edge if there are VMs from a particular compute cluster that mounts VHDs from another storage cluster. And for each edge, we'll compute a weight, which is basically the fraction of VMs that have crashed due to VHD failure access failures for a given window of time. Now we can better visualize this bipartite model using a two-dimensional grid. And the color here will indicate the VHD failure rate. Now this model might seem really simple, but once we put production data in it, some failure patterns immediately jump out at us. For example, when we have compute cluster failures, what we'll see is that we typically get a row of red cells pointing the finger at the faulty compute cluster. In other cases, when we have storage cluster failures, we'll typically see a different type of failure pattern, where we get a column of troubled cells with a mix of failure rates. So once we have seen that the Azure measurements reveal those kind of common failure patterns, we're convinced that our approach is promising. But to put this idea into production use, we need to solve a few remaining challenges. The first one is, when the network fails, we want to be able to actually pinpoint which part of the network has failed. And for that, we need to generalize our model to actually include the network. Second, what kind of algorithm should we use to identify the failure patterns, especially given that the gray failures are very hard to deal with. And to do that, we'll propose a hybrid algorithm incorporating Lasso regression and hypothesis testing. Finally, for the system to be useful and practical, we needed to operate in near real time. And for that, we'll design and implement a streaming data pipeline that's able to get us results fast. So to summarize our goal, we want a system that's able to localize VHD failures to the underlying failures in compute, storage, or network subsystems within a time budget of 15 minutes. Next, let me describe our model and algorithm. So we want to generalize the model, the bipartite model, to include the network. And at a high level, we're basically replacing the bipartite edge with a network path from compute to storage. However, we immediately run into a complication because there are multiple paths, and the use of ECMP obfuscates which path is being used for any particular VHD request. So our solution is to simplify the cross network to a tree so that there's a single unique path from compute to storage. We also note here that we can model at different granularities, whether at the level of clusters or racks, and the models can generate easily. Now, the goal of the algorithm is to be able to pinpoint which subsystem along the path is responsible, and then try to isolate as fine-grained as possible to the particular component within that subsystem. So to be able to tell which component is responsible, we can estimate the component health. We can write down a simple probabilistic equation where let's assume that components from different subsystems fail independently. Then we can express the probability that the path is healthy as the product of the probability that each of the components along the path is healthy. Now we will use blue to denote observables, red for unknowns, and purple for what's given by the topology. We can estimate the left-hand side of this equation by 1 minus the fraction of failed VMs. Then to make this equation more mathematically tractable, we take log on both sides so that we turn the product into a summation, and then we get a system of linear equations. Now, if we're able to solve those equations exactly, we will be able to get those PJs, which are the component health probability that we're after. However, because of measurement noise, we actually can't solve it exactly. So what we have to do is to turn it into a linear regression problem, where after change of variables, we get these regression equations where we have to solve for beta j's. If you can get a beta j, you can easily compute PJs. So for example, if the beta j for a component is 0, that means that the PJ is 1, which means that the component is definitely healthy, and we shouldn't blame it. On the other hand, if beta j is much less than 0, by using the data to estimate, then the PJ is very close to 0, which means that the probability that the component has failed is very high, and we should blame it. When we try to apply those linear regression equations on a realistic topology, we run into another problem. So what happens is that the kind of topologies we run into in production may cause us to have more number of unknowns than the number of equations. And in those cases, we wouldn't be able to solve the equations. Also, traditional least square regressions would not be able to give us an answer. To get an idea of that, you can look at the example topology on the right side here, on the right here, where we have 5 unknowns but only 4 equations. So you just can't solve them. But we also know from experience that multiple simultaneous failures are rare within a short period of time. So is there a way of encoding this domain knowledge mathematically that can help us solve those equations? Well, as it turns out, that asking failures to be rare is equivalent to be preferring most of the beta j's to be 0. And Lasso regression is one particular well-known technique to get sparse solutions efficiently. So what Lasso regression does, compared to the traditional least square regression, is that it adds an L1 penalty term to the objective function so that it forces a lot of those beta j's to be 0 and selects for a sparse solution. So now the first part of the algorithm estimates component health probability. But what we really want is a binary decision as to whether flag or clear each component. While we can use ad hoc thresholds, they don't tend to work reliably. So we wonder, is there a way to make a decision for each component in a principled and automatic manner? By playing around with the data, we realize that if the estimated failure probability for a component is worse than average, then it's likely a real failure. So now we have this empirical decision criterion, which we can automate using a hypothesis test. Well, basically now we're using data to decide between two competing hypotheses, where the null hypothesis says that the estimated failure probability is average, or versus the alternative, which says it's worse than average. So if the data allows us to reject the null hypothesis, then we have good enough empirical evidence to blame the component J. Otherwise, we should clear it from blame. Now, the core of our Deepview system consists of a near real-time data pipeline, where we have to collect two kinds of data. First, we need to get those VHD failure events from the hypervisor log. Then we need to take periodic snapshots of various kinds of VM metadata. We will then ingest those raw data into an internal log analytics platform called Qiao. We implement a near real-time scheduler that runs a set of database queries periodically in the right order so that we can stream a sliding window of input to an algorithm. And then the output of the algorithm is written back to Qiao for downstream consumption, such as sending alerts to SREs or visualization. Now I'll move on to the evaluation. So Deepview has been deployed in production at Azure. We asked three questions to evaluate it. First, how well can it localize VHD failures in production? Second, how accurate is the algorithm compared to alternatives? And finally, how fast is the system? To evaluate Deepview's effectiveness in production, we'll present some production case studies. Here are some simple statistics. We analyzed Deepview results for a month, where the daily number of VHD failures vary from hundreds to tens of thousands. Deepview is able to detect 100 failure instances, where 70 of them can be matched with existing tickets, while the rest were previously undetected. Deepview is able to reduce unclassified VHD failures from tens of thousands to less than a max of 500 per day. So for those remaining failures that we couldn't classify, they're mostly due to single host failures or customer mistakes. For example, customers trying to mount VHDs from using expired storage accounts. Next, I'll talk about three concrete case studies of the kind of failures that Deepview is able to uncover in production. So the first case study concerns unplanned ToR reboots. We know that ToRs can reboot unexpectedly, which brings down a whole rack of VMs with it. While we know that this can happen, we don't know where and when as it happens. Fortunately, Deepview is able to flag those ToRs as they crash. So the figure on the right here shows that in one small region, when a ToR crashed, Deepview is able to blame the right ToR among a total of 288 components. So what can we do now that we couldn't do before using Deepview? Is that we're now able to associate VM downtime with ToR failures. You couldn't get this by just looking at the logs on the switches. This data allowed us to quantify for the impact of ToR as a single point of failure on VM availability, which we'll talk about soon. The second case study concerns storage cluster grade failures. So we know storage clusters can fail in a way that only impacts a subset of VMs. So in one incident, a storage cluster was brought online with a software bug that puts some VHDs in negative cache. So as you can see from the graph, as time progresses, more and more VMs were impacted by this software bug. In this case, Deepview is able to flag the faulty storage cluster almost immediately, while manual triage process took 20+ hours. Finally, let's look at network failures. So we know wide impact network outages are rare these days, but they do still happen. So in one recent incident, due to operator mistakes, a number of top-tier network links were mistakenly shut off, causing a large capacity loss. This didn't cause any disconnectivity, but when background storage replication traffic hit those network switches, it caused huge amount of packet losses and caused many VMs to crash. So in this case, Deepview is able to pinpoint the misbehaving aggregated set of switches. Now let's compare Deepview's accuracy with alternative algorithms. We picked two other representative tomography algorithms. So Boolean tomography and SCORE both use greedy heuristics to find a minimum set of failures that can explain the observations. We'll compare them using production trace from 42 incidents, and we'll compare them in terms of precision and recall. What we see from the graph here is that Deepview is able to achieve both higher precision and recall compared to the alternative tomography algorithms, which use greedy heuristics. Finally, let's look at how fast Deepview is. So the metric we care about is time to detection, which is the time from when an instance starts to when the failure is localized. We can estimate the instance start time by looking at the timestamps on the VHD failure events, which we collect from the hypervisor logs. What we see is that Deepview is able to consistently achieve a TDD that's under 10 minutes, where the data ingestion part takes about 3.5 minutes. The sliding window delay is about 5 minutes, while the worst-case algorithm runtime is less than 20 seconds. And Deepview is able to actually meet the production target of 15 minutes. While we know that we can perhaps make the system faster by a clean slate design, but mitigation time itself is on human timescale, which are on the order of minutes. Now I talk about some of the architecture lessons we can learn using Deepview's data. So in general, system designers have to balance various trade-offs as they design practical systems. While in many cases we know what those trade-offs are, we can't quantify them. So here we show that for 2 design decisions, using Deepview's data, we're able to actually quantify those trade-offs. So the first one tries to quantify the impact of ToR as a single point of failure. As we all know, data center designers choose a single ToR per rack to reduce networking cost. But what is the impact of that on VM, since now ToR become a single point of failure? Now we can finally use Deepview's data to actually quantify that impact. So from our data, we see that there are 2 types of unplanned ToR failures. There's the soft failures, which can be recovered by simply rebooting the ToR, versus the hard failures, which require the ToR to be manually replaced. So we can actually calculate ToR availability, which is basically 1 minus the expected downtime divided by a total amount of time. From data, we know that 90% of ToR failures, unplanned ToR failures, are soft failures, and each of them can take a maximum of 20 minutes, while 10% of ToR failures are hard failures, which can take up to 2 hours to be replaced. Out of a fleet of tens of thousands of ToRs, about 1,000 of them would crash per month. So if you do the math, ToRs can achieve a maximum availability of 6 nines. And as a rule of thumb, we will require dependent services to provide 1 extra 9 to the target service, which means that 6 nines from the ToRs should ideally be able to support 5 nines from the VMs. To put this in another way, it means that ToRs are actually not on a critical path for VMs to achieve 5 nines availability, despite being a single point of failure. Next, we'll try to quantify another design decision, whether we should co-locate VMs and their storage. So at Azure, we allow VMs to mount VHDs from any storage cluster in the same region. And this is because we want to get maximal load balancing. What this also means is that for some VMs, they'll have storage that are further away. So we wonder, can a longer network path impact VM availability, and by how much? We use our data, and from our data, we see that about 52% of VMs have storage that are 2 hops away, and 41% of them have storage that's 4 hops away. And we compute the daily VHD failure rate for either cases, and we take an average over a 3-month period. We're able to see that for those VMs that access storage that are 4 hops away, they see an 11.4% increase in VHD failure rate. What this means is that a longer network path do lead to higher VHD failure rate. And in this case, using Deepview's data, we're able to quantify that. So there are 3 main related work to Deepview. The first one is NetPraru from SIGCOMM 2016. It proposes a single node solution for failure localization using TCP statistics. We believe that it's complementary with Deepview if we're able to obtain TCP statistics from customer VMs. The second related work are binary tomography. And for this set of algorithms, we're able to show that Deepview can actually achieve higher precision and recall in experiments. Finally, there's the use of Bayesian network for failure localization. Despite trying really hard, using various kind of approximation techniques, we still find Bayesian network to be too slow for our problem. And it is our future work to compare accuracy with them experimentally. In conclusion, we've identified VHD failure as the availability bottleneck at Azure. We introduced a system called Deepview that's able to reduce unclassified daily VHD failures from tens of thousands to hundreds. Deepview is able to review new interesting failure patterns, including unplanned ToR reboots and storage cluster gray failures. And finally, using data from Deepview, we're able to quantify the impact of several architectural decisions on VM availability for the first time. Thank you, and I take questions from here.
Feel free to come up and ask questions. In the meantime, while you're formulating your questions, I will ask, is there a cause of VHD failures that is seemingly the next thing to work on, the one that you can't quite diagnose well, but you think that we should be able to?
So we did say that there's a set of failures that we currently couldn't localize, including single host failures. Right? If a single machine goes down or the hypervisor having some issues, just because we don't have enough VMs on those machines, we won't be able to have enough information to actually correlate and tell them, localize them. But I'm not quite sure whether that's we don't actually have data to know whether that's the bottleneck that we should work on next, because now we have dealt with the bulk of VHD failures. The remaining ones might no longer become the availability bottleneck for Azure.
I was also wondering whether Lasso regression does well or is able to detect it when there are 2 or maybe even 3 correlated failures.
Yeah, so that's a very good question. So typically, this is the hard point for a lot of tomography algorithms. Basically, you have to assume that there's a single failure, and if there are a lot of them, then it becomes really hard. I would say that in practice, failures are pretty rare. So it's kind of hard if you're just looking at 1 hour period of time for a region. Typically, it's only a single failure. But if there are multiple failures, I think there's no theoretical guarantee from Lasso that it can give you all the failures. But if it is the case that there's only a single failure, then you should be able to pinpoint it.
Hi, Ajay Mahimkar, AT&T. So can you give us some intuition as to why Lasso did well as compared to SCORE?
Oh, sure. So if you look at SCORE and various kind of tomography algorithms that's been proposed, in the community, it does a lot of heuristics, right? Basically, you're either doing voting or using filtering, various kind of heuristics to sort of filter out noise. But what Lasso did, or what our approach did, was basically took a probabilistic approach. Rather than saying if the component is either down or up, you're looking at the probability that it's actually healthy. And then you're trying to estimate that using regression. And why Lasso particularly works well is that in practice, when you only have a couple of failures, like failures are actually rare, Lasso regression is particularly good at uncovering this kind of failures. It just matches with the assumption of the algorithm really well.
But in your experience, have you seen scenarios where, you needed probability to tell you that this particular VHD failed? Is it usually just 1, or do you see 0.5% times it goes down? So where is probability going to help?
Oh, so I said the algorithm has 2 parts, right? The first one is estimating the probability for each component. The second part is trying to binarize the decision. But if you start with a binary state for the thing, you're actually losing a lot of information. Okay. And that's why I think the intuition.
Last question. Real world missing data and delayed data is a big challenge,
yes.
Right?
Yes.
So you said real time collection and assessment of this, right?
Yep.
So have you thought about robustifying your technique to deal with missing data or delayed data?
That's a very good question. So currently we leverage the existing data pipeline, ingestion pipeline, and processing from already provided by Azure. And part of that system, data ingestion is to deal with delayed data as well as missing data. So the data input part is taken care of. In terms of algorithm, I think if we can get enough information from a lot of VMs, like if you just take a lot more data, then it itself is actually pretty robust.
Hi. So quick question for you. So for other probabilistic models like Sherlock and those approaches that are actually probabilistic rather than tomography approaches, do you have any comments on those?
Yes. So there are a whole bunch of approaches that are probabilistic, but they're doing Bayesian network. So there's a huge amount of promise using Bayesian networks, right? It's very expressive and it's elegant and all that. But in practice, if you're looking at applying Bayesian network for real problems, once you have enough components, it becomes extremely slow. And so what people have done is that they try to propose various kind of approximation techniques. Well, but depending on the problem itself, sometimes it's fast enough, but sometimes it's not. And we realized that for our problem, despite trying very hard, like various kind of approximation, it's just not fast enough. So, thanks.